For number 13 on page 177, what we're dealing with is, here's our system. With our system being like this, we have a mass 2, a mass 1, and this angle theta at 30 degrees. And we have these two blocks, and they have all this words in here, so we're going to try to use that. What we're going to try to first get is a free body diagram. So I tried drawing up my system as well, where I have a mass 1, mass 2, and my angle theta. That theta is going to be at 30.0 degrees. It said there's no friction from the pulley, and there's also no inertia that pulley is going to affect on the system. The force due to friction from the surface is going to be 0 newtons. So that friction is relatively negligible, as it says. So I tried making free body diagrams and also indicating where I think this is going to accelerate. So I have to say that this is going to accelerate this way. So that way I can get my acceleration for my system here for my first free body for mass 1 falling down. So I have my mg down, that's that gravitational force down, and that tensional force up. For this second mass, what we're going to get to is I'm taking this and I'm making the tension, which is going up at this angle. I'm going to take that and I want to make it lie along my x-axis. So what I do is sometimes I draw over on the side my surface, and I draw the block on the surface, and I know I have gravity coming straight down for object 2. What I'm going to do is I try to rotate it, so that way now I have that flat surface, and my gravity is coming off at this angle. So that's why I drew that flat surface, and my gravity coming off at that angle. So now I have my gravity coming off at that angle. So I try to draw that, and I know the angle I had to move is this angle theta. So now we're going to have gravity in the x and gravity in the y, with tension only in the x and this normal in the y. And I made this mark right here because this tension is going to be the same tension for both object 1 and object 2. So that's going to lead us now to that expression of the mathematical part. So now we're going to take these free body diagrams and break this up into the x and y components. There's no forces in the x direction for mass 1, so the sum of the forces in the x is 0. We're trying to find the net force, which is equal to ma. So the sum of the forces in the y direction is tension up minus mg down equal to this negative m1 times a. I'm saying that this is going down as negative. In the back of the book, it says down is positive. You can change your coordinate system. I like to just keep my coordinate system the way I like to think of it, as up as positive and to the right as positive for object 2. If you go with a different coordinate system, you just have to keep yourself in the same coordinate system. I like to work with the same one that I've always worked with. So I know then for object 2, I'm going to have my mg in the x direction minus that force due to tension. That equals to ma. It's going to accelerate if we're saying it's going to accelerate, and if it's accelerating, now it's going in this negative direction because of how I assigned it before, where I said everything is going to be going this way. So then it says in part B, the acceleration of the system is going to be 0, and we want to know what m1 is. So in order to do that, we're going to do the same thing where I'm going to solve for that force due to tension in the first object, because I know the tension is the same tension, so the tension in the first object is just m1 times g, because it equals to 0. I'm just taking this right from up above. Now we set a equal to 0, so this is 0. So the force due to tension is just mass times gravity. Then I take the tension, I bring it over to what I have for my second object. I know my m2 times gx minus this tension now is just this, which is m1 times g, is still equal to 0 because the system is not accelerating. So now I can figure out what my mg in the x component is. Well, this is that x component. It's the opposite of that angle, theta. So some old hippie caught another hippie. This is opposite, so sine of theta. So I'm going to use that sine of theta. multiplied by g. And now we have this expression here which equal to 0. I'm going to set this mass equal to the mass because I'm moving 1 to the other side. I'm moving m1 times g to the other side. You can divide by g, leaving us that m2 sine of theta, which is 30 degrees, and sine 30 is 0.5, is equal to m1. So m1 is 0.5 of m2. So we see that this mass 1 is half of mass 2. Then it says in part C that this theta, which was 30 degrees, is now moved to 20 degrees. And we also know from this that this mass 1 is still half of mass 2. So what we've got to try to find is this acceleration, so we can plug it into this, x equal to 1/2 at squared plus the v naught times t plus x naught, where the v naught is 0. So really we've got to find a to plug it into here. So we have this time-dependent equation here for the displacement of the block. So we know that x equals to 1/2 at squared, so we got to find a. So we're going to start back with the equations that I got in our first one, where this tension minus the gravitational force is equal to ma. That mg in the x minus the tension is equal to ma. That's from that free body diagram from part A. We're going to do the same thing where we're going to find that force due to tension, solve for the tension, but now we have this acceleration term, and now we're going to plug it in over here. So then this equation on this right-hand side, it becomes now this m2 times g sine theta, that's still there, minus that force due to tension, which is m1 times g minus m1 times a. So then that negative sign distributes throughout, where it's now negative m1 times g plus an m1 times a. I'm going to move this m1 times a to the other side. I want to get all the acceleration on one side of the equation and keep the g's on the other side of the equation, because now we have m2 g sine theta minus m1 times g. That equals to this negative m1 times a, negative m2 times a, where I'm able to now pull out the g and pull out this a, where this a is then a negative sum of the masses. I just have this negative term. I put it here with the a, keeping the sum of the masses. So that way I can have my negative a equal to that term divided by my sum of the masses. And I'm going to then multiply both sides by a negative to give me my m1 minus m2 divided by the sum of the masses times g. And now we have that expression. Now that we have this expression here in terms of g, mass, and theta, so we know that m1 is half of m2. So we're going to divide mass in kilograms divided by kilograms. So once again, we're getting a ratio. Kilograms will cancel out. So I'm just going to set this to an arbitrary 1. I put kilograms because I think that helps us understand a little bit. If I know the mass is 1 kilogram, then the second mass, well, if the second mass is 1 kilogram, then I have the first mass is half of that, 0.5 kilograms. And that's what we got from letter B. So then I plug in for m1 is 0.5 minus 1 times a sine. The sine now is sine of 20 divided by the sum of the masses, 0.5 times plus 1, times g, where I know sine of 20 is this 0.342. So then this 0.5 minus 0.342 is 0.158 divided by 1.5 times g. I get my acceleration is 0.105 g. Now I should actually use sig figs and have this 0.11 times g and be consistent, getting that my x is 1/2 at squared, 1/2 of my 0.11 times g t squared.